Hello students, welcome back to another video lecture on quantum mechanics. So in the last video lecture we have seen what exactly quantum mechanics, and we have seen what are the fundamentals and classical mechanics and quantum mechanics difference. Then we have seen what is wave particle dualism and de Broglie hypothesis, and finally we have seen Heisenberg uncertainty principle, and we have also understood the difference of measurement in the case of classical and quantum. So also we understood what is the accuracy or probability of finding. In this video lecture we are going to see wave function and its significance. Also it's known as a Max Born interpretation. Okay. The quantity that is a matter wave or de Broglie wave that varies periodically, called wave function. The quantity varies periodically. The matter wave or de Broglie wave, the quantity varies periodically, is called as wave function. Usually complex function is a wave function is a complex function, and it consists of both real and imaginary part. Hence psi, generally we represent wave function as psi, by itself cannot be observable quantity, because psi itself has no physical interpretation. But of course, square of the absolute magnitude, that is modulus of psi square evaluated at a particular place at particular time, is proportional to probability of finding particle, that at that time. So a probability is, however, must be a positive and real quantity, that is whatever I am talking about, modulus of psi square is equal to psi star, where psi star is nothing but a complex conjugate of psi. Psi star is complex conjugate of psi. The quantity psi modulus of psi square is called as, or psi star is called as, probability density. That is probability per unit volume. The probability of finding the particle in given region of volume, that is we generally say dV, given volume, the given region volume dV, containing a point r, is given by psi of r comma t modulus whole square dV. Since particle is certainly somewhere in the space, so somewhere in the given space or region, so therefore probability, if particle is somewhere in the region, then probability p is equal to 1. That is nothing but, that is represented as integral of psi of r comma t whole square dV. So that is triple integral minus infinity to plus infinity modulus psi of r comma t square dx dy t set that's equal to 1. That's equal to 1. The meaning is you can find that means you can find the particle somewhere. So probability 0, suppose this is equal to 0, meaning you suppose this is equal to 1 means you can find particle. 0 corresponds to certainly you cannot find the particle. So to understand better, let us understand what exactly normalization of wave function. So probability density is given by psi of r comma t whole square. The probability of finding particle in a given region of volume dV containing point r is given by psi of r comma t whole square dV, just a few minutes before we have seen. So therefore total probability overall space is P of r comma t, that is given by integral minus infinity to plus infinity psi of r comma t modulus whole square dV. Since a particle is certainly found somewhere in the space, we have so this integral can be written as triple integral minus infinity to plus infinity psi of r comma t modulus whole square dx dy dz, that is equal to 1, because you can find somewhere in the particle probability is equal to 1, so that means you can find. So the condition is referred to be normalization condition, and we have function that obeys the equation of normalized, so this is called as normalized. So that therefore if triple integral, that is volume integral psi star dx dy dz is equal to 0, that means particle doesn't exist, particle does not exist. So that is if, suppose if same integral psi star dx dy dz is equal to infinity. So meaning is particle is everywhere simultaneously. So that's possible only in quantum mechanics. The particle is everywhere simultaneously. So all point. So that means we have to understand. So particle, that is probability is equal to 1, means particle exists somewhere. If it is equal to 0, particle doesn't exist. If it is equal to infinity, particle exists everywhere simultaneously. So let us try to understand properties of wave function. It's also called as condition for well-behaved wave functions. So there are mainly 3 properties for wave function. The first one is wave function psi must be finite. This should be finite, single valued and continuous everywhere. That is the first condition, first property of wave function, continuous everywhere. That's very, very important property. The second one is the partial derivative of the wave function, that is dou psi by dou x, dou psi by dou y and dou psi by dou z must also be continuous, also be finite, single valued, continuous everywhere. It also should be finite, single valued. If psi also finite, the wave function also finite, single valued and continuous everywhere. It's the same manner. Partial derivatives dou psi by dou x and dou psi by dou y and dou psi by dou z, this should also be finite, single valued and continuous everywhere. And finally, the third property, psi must be normalizable. Must be normalizable. Psi must be normalizable. So that is, meaning is, normalizable means the total probability P of r comma t is equal to integral minus infinity to plus infinity modulus of r comma psi of r comma t whole square into dv, or that's equal to triple integral minus infinity to plus infinity psi of r comma t whole square dx dy dz is equal to 1. So the probability of finding is equal to 1. Next, let us move on to Schrodinger wave equation. So Schrodinger wave equation, we are going to see there are different types of Schrodinger equation, time dependent, time independent. We are going to see time independent. Time independent Schrodinger equation for a particle, that's very important, in one dimension. So we start with one dimension, later of course we can extend to 3 dimension. So let us see how exactly the equation of Schrodinger equation for particle in one dimension. The wave equation for de Broglie wave traveling in positive x direction can be written in a complex notation as psi is equal to psi naught e to the power I kx minus omega t. Where psi naught is a amplitude and k is equal to k is equal to 2 pi by lambda and omega is equal to 2 pi nu. So in the x position coordinate at time t. So differentiating. So let us differentiate equation 1 with respect to x. Differentiating with respect to x. So d psi by dx is equal to psi naught I k e to the power I kx omega t. Correct na? On differentiation, psi naught is a constant. E to the power I kx minus omega t is differentiation is same. Again you have to differentiate exponential term. So power. So you are left with this is a constant, it becomes 0. So you are left with ik, x is 1. So this can be written as, x can be written as, Here psi naught into e to the power I kx minus omega t is nothing but psi. So therefore you can write ik into psi. Ik into psi. So let us differentiate, find out second differential, that is d square psi by dx square. Again you are differentiating with respect to x. So then it's nothing but ik, k is a constant, d psi by dx, d psi by dx. d psi by dx is nothing but ik psi. So therefore it is ik into psi, or simply it is d square psi by dx square is equal to I square k square psi, k square psi. In other words, d square psi by dx square is equal to k square. I square is nothing but minus 1, so therefore minus k square psi. I got second differential. Why this is? Because already told, because I is equal to root of minus 1. So I square is minus 1. Let us substitute the value of k in the above equation. Just few minutes before we have seen value of k, that is k is equal to 2 pi by lambda. So substituting in equation 2, we get d square psi by dx square is equal to minus will remain as such, k is equal to 2 pi by lambda, k square becomes 4 pi square divided by lambda square into psi. So let me rewrite. 1 by lambda square is equal to, rewriting this, lambda square is equal to 1 by minus 4 pi square psi d square psi by dx square. Call this as expression 3. Okay. So now we know that the kinetic energy of moving particle of mass m, kinetic energy of moving particle of mass m and velocity v is given by kinetic energy k is equal to half mv square. This is well known fact. So this can be written as kinetic energy is equal to, I will rewrite this as m square v square divided by 2m, dividing and multiplying by m. So m square v square is nothing but, mv is nothing but momentum, so therefore p square by 2m. So de Broglie wavelength, from de Broglie wavelength we know de Broglie wavelength is given by h by p, or momentum can be written as h by lambda. So let us substitute that same in equation 4. Substitute this in equation 4. So therefore kinetic energy is equal to p square by 2m, that's equal to h square by 2m into lambda square. Call this as 5. So 1 by lambda square, you have equation 3. You have value from the equation 3. Let us substitute from 3 in equation 5. So you get kinetic energy is equal to p square by 2m, that's equal to minus h square by 8 pi square m 1 by psi d square psi by dx square. So let us consider the particle is moving in a field of potential V. Then total energy of the particle is given by total energy that is E is equal to kinetic energy plus potential energy. So therefore E is equal to P square by 2m plus V, or P square by 2m is equal to E minus V. Rearrange. Okay. So on substitution the value of P square by 2m, we will get minus h by 8 pi square m 1 by psi d square psi by dx square is equal to E minus V. So just rearranging the terms, so we will get d square psi by dx square is equal to 8 pi square m divided by h square E minus V psi. So just further rearranging, taking to the left hand side, you will get the expression as d square psi by dx square is equal taking left hand side, so therefore plus 8 pi square m divided by h square into E minus V psi is equal to 0. So this is the desired Schrodinger wave equation. This is a time independent Schrodinger wave equation. This is the desired equation. Let me call this as equation 6. This is the desired equation. So of course we have to find out the solution for this Schrodinger wave equation, that is known as eigenfunction. Solution is called as eigenvalue. All those things we will discuss in the next video. Here I will stop. Thank you for watching.